Down here is the white dwarf branch. Sirius B, this year's deep sky object, is a white dwarf, sits right about here. Like I said, this is a cartoon. The white dwarf in NGC 2440 is about 200,000 Kelvin. It is the hottest object. But white dwarfs also cool off over time, get dimmer and dimmer. These here are older and dimmer. The newer ones are forming here. And so we have the white dwarf branch. And you can still plot a white dwarf on the HR diagram, usually. Now, there are different kinds of white dwarfs. Don't think that a white dwarf is just this thing of carbon. Okay, there are, of course, different flavors. Different things can happen to white dwarfs. Actually, when I said fusion stopped at carbon, that's not so. If you have a really upper limit white dwarf, then carbon can actually fuse, but neon can't. So if that happens, you're going to have an oxygen neon white dwarf. Otherwise, a run-of-the-mill white dwarf is carbon oxygen. But they can also have, depending upon the circumstances that form the white dwarf in the planetary nebula, they can also sometimes have a carbon or a neutral helium atmosphere, quote unquote, around the white dwarf. So white dwarfs are a lot more complicated and complex than we are led to believe. So here we go. So a white dwarf is sort of like, you know, the old, you only live twice? You're too young to remember that, right? 007, Sean Connery, yeah, some of us remember that. One of the movies was You Only Live Twice. Well, this is a star that gets to live twice, because one would think, oh, I'm a white dwarf now. I have to sit here for 1 trillion years and just slowly fade away. But if you happen to be in that binary system with a companion star, and they are close enough for contact to be made at the Roche limit, and material can start to accrete into an accretion disk around the white dwarf, then you have that possibility of ending up being something else. A type 1a supernova event. So here is Tycho's supernova event that he saw in 1572. And actually this is kind of a really important object because this is about the time when astrology started transitioning into astronomy, and a major paradigm shift in our thoughts about the universe, and we started actually observing and recording data during this era. This is the destruction of a white dwarf that he saw, and it's been observed several times, and you'll see this odd little kind of arc right there. This is a Chandra image. It's an X-ray image. It has been calculated that the center of the explosion is right there where that little green pointer is. Where the supernova explosion happened, it had a companion star, of course, and that companion star was oriented right here. And when the white dwarf had accreted enough material from its companion star that there was no choice but to undergo a thermonuclear explosion, the blast hit the companion star, gave it a boost in velocity, so it has a different velocity, changed its direction of motion, and blew off some of the atmospheres of its companion star, blew it out to here, and that's what this arc is, and you can actually see the shadow underneath the debris that was thrown out by that star. The companion star is this one right here. That one was observed by the William Herschel telescope. It's a UK telescope in the Canary Islands. They're 4-meter scope. So they do believe they have finally found the companion star for Tycho's supernova remnant. Here is another one. This is Kepler. In 1604, Kepler observed this one. It's also a type 1a. Since a type 1a is much, much brighter than the core collapse of a massive star like the other ones that we're not dealing with this year. They are very, very bright, so if they are close enough, you can see them. It would be nice if that was going to happen to Myra, because it's fairly close. We could actually see that, but I don't think it's going to happen. This one is actually in the Large Magellanic Cloud. It's 160,000 light years away. The blue stuff is X-ray radiation from this event. The pink corresponds to the highest X-ray emission. That's the shock wave moving out. The pink is a Hubble observation. It's the shocked material from the event. And you see, when you have a type 1a supernova event, all you have is the remnant. There is no stellar core. Now here are DEM 238 and 249, and you will see this is kind of a different look. But here's DEM L238. Now look at all this green. That's iron, an extraordinary amount of iron. Now if you have a thermonuclear explosion, even though that white dwarf only had up to like carbon, neon, oxygen in the core, that explosion is going to cause fusion to start all over again, and it will fuse heavier and heavier elements, and you will have iron and everything else in a type 1a supernova remnant, even though they weren't in the white dwarf itself. And so look at the difference in these remnants. It is thought that this one, Kepler, which has a lot of iron in the center, and this one, DEM L238, which has a lot of iron in it, where this one doesn't. It has an even distribution. This has an even distribution. It is thought that these were much more massive, therefore they were younger, and there was a lot of stuff around them when they underwent their explosions, and so they're a little bit different than the others. There are different types of type 1a events. Now, we have mentioned RR Lyra variable stars and type 1a supernova, and both of those are used to calculate distances to other galaxies and galaxy clusters up to 10 to the 10 light years away.